So, hello everybody again. In my slot, I'm going to present an ongoing work on TVB multiscale toolbox, which is again a toolbox extending TVB scripting in order to interface it with spiking network simulator NEST in order to perform multiscale co-simulation. So first, I'd like to make more specific what we mean by co-simulation. So as you know, well, we have seen today all the great benefits of TVB as a large-scale simulator of the brain. However, there are times that we really want to focus on some neural mechanisms like synaptic plasticity, and therefore we would like to be able to interface such a model with spiking network models and have a reference of them being at specific parts of the brain. The main message I want to convey here is that the whole co-simulation implementation that we've done until now focuses on the population level. In other words, the interface happens at the level of populations of neurons, because there we can draw a mapping between state variables of the mean field models of the virtual brain, which summarize anyway the activity of neural populations at the mean field with the average activity of spiking networks, populations of spiking networks. So the structure, the coding of the toolbox is taking a little bit of a TVB user perspective, as you're going to see. So for instance, the neural networks, the spiking networks parameters are informed by the model that one chooses from TVB, and all the mappings are drawn, as I said, from mean field variables to populations. You're going to see this through the API I'm going to show you. So first, a few words on the structure of the software, which you can find in GitHub, and also there are a couple of Docker images at Docker Hub. Sorry, I didn't want this to happen. Okay. So first, there is a part of the toolbox that is the largest also, which extends TVB in order to perform multi-scale co-simulation, a bit irrespective of which spiking simulator is chosen, although for the moment it works only with NEST. So this part contains spiking models. So in addition to the TVB models we know then, we add spiking models, which consist of spiking, a class that represents a spiking network, which in itself is a collection of region nodes and stimulation or measuring devices, so that we can stimulate the spiking network and also observe its activity. Region nodes, on the other hand, are collections of populations of neurons. And also there are classes of builders that help the user, a TVB user who is not a specialist with any spiking simulator, to define his models, draw parameters from TVB, and eventually build such a spiking model. However, in principle, one could skip the use of these builders, build his own favorite spiking model, and then just make sure of a few hooks in order to interface it with TVB. Second, there are models of interfaces, models of coupling from TVB to the spiking network, and models of updating the TVB state from the spiking network. This is an important part as well, that in any case, the integrity of the TVB model is maintained. There is no hole in the TVB brain because it's simulated in a spiking network. At every time step, we recover the activity for the whole brain. Therefore, the coupling from the spiking network to the TVB is in the form of an update and overwriting the activity, not of coupling. And again, there are builders who can help the user make a few choices and build his own models. There are minor parts of the code. There is similarly a builder to help configure the TVB simulator for this kind of simulations, and other scripts to help you plot, write files with the results, analysis, etc. Then there is a specific implementation of all this as an interface to NEST through its Python interface, PyNest. So NEST is a state-of-the-art simulator for spiking network simulations. And yeah, so this second part inherits from the general classes and makes the specifications that will make it work with NEST. It is an ongoing development, so there is no much testing for the moment. We are in the process of validating everything. Still, there are some examples, there are some tests, there is some documentation, additional scripts that help do small parts of the job. And as I said, also a Docker file to build a Docker image. While now I'm trying to start using more Elephant for some aspects of the toolbox, like for generating stimuli, for the spiking networks, or for some part of the analysis. Right, so the usual workflow for a user would be to define some configurations. There is already an informative configuration, but the user can change part of or everything from it. Then first of all, build the TVB model and simulator, configure it in the usual case, like for any TVB simulation. Then it follows the part of building the spiking network model, which, as I said, in principle can be skipped and done independently. As long as in the end the spiking network can be integrated to the spiking network models I showed you before. Sorry, then there is a step 4 where the building of the interface is performed between the two models. And finally, there is the simulation, and then the user can gather results and analyze, plot, etc. So there is a full developed use case going through these steps as a Jupyter notebook in the eBrains collaboratory. It would take a lot of time to go really step by step through it, so I'm going to focus on the most important aspects, namely the interfaces. And depending on the time, I'm going to show you more or less details of it. But you can anyway find the notebook and run it. And actually, it has a lot of code commended because, in principle, the simulation can be run on a very informative, very informed manner by the default builders with just a few lines of code. But then in the commended part, the user can see some of the different options he could change on these builders in order to adjust his model. So a potential user, just like in TVB, that usually he can inherit some of the existing neural feed models and change or copy paste and make his own models. Similarly here, the user can inherit either the spiking models that are builders that I have already constructed, or interfaces, and adjust them to his own needs and models. So I'm going to go, as I said, through parts of the code of this use case. In this use case, we assume that there is one excitatory and one inhibitory population at every node of the brain. And there are the mean field nodes are modeled with a reduced Wang model, and the fine scale ones in NEST. There I'm using a spiking neural model, which is very similar to the original Wang model, with a few approximations so that it is modeled in NEST. So, as I said, the most important thing is how to do the interface between the two simulators. And first of all, how to couple TVB activity towards nodes of the brain that are modeled as spiking networks in NEST. So the main idea here is to create what is called a proxy node, a TVB proxy node inside the spiking network. These are nodes that mimic the activity of TVB and accordingly convert it to something NEST can understand, the spiking networks can understand, and stimulate the spiking networks that exist in NEST. The most usual case is where we take a state variable from TVB that represents rate and convert this to spike trains in order to stimulate the spiking networks. For this, for the moment, we are using NEST devices that can generate spikes like Poisson generators, Poisson spike generators. And in this case, such devices that are created inside the spiking network are connected to the regions that are modeled in NEST with time delays and potentially connectivity weights derived automatically from the TVB connectome. Therefore, here, the delays are taken care by NEST itself. Now, to define such an interface, it's as simple as a few lines of code, which are more here because the example is a bit complicated and there's a lot of comments. But in principle, one defines a Python dictionary with several properties. The most important of them is to choose the specific device of the spiking simulator, here an homogeneous Poisson generator that can generate spikes, pass on any parameters that are specific to this, define a weight that could scale the TVB activity before passing through the interface. Then there are these two arguments, weights and delays, which are define how the TVB connectome is going to take in consideration. Here one can define functions that take as arguments the node IDs of its region, and accordingly can generate a weight, for instance, as a normal distribution around the TVB weight. Similarly for the delay. Also, different synapses can be defined for the different incoming signals from different TVB nodes as different receptor types. The most important, though, property here is the connection, which defines the mapping between the TVB state variable and the target population of the spiking network. So here we're just saying that the instantaneous rate activity from TVB should create spikes that couple to the excitatory population of the spiking network. And this can be homogeneously created among all pairs of nodes between TVB and NEST, or one can define specific subsets of them. And by defining several interfaces like this, we can have an heterogeneous interface for different brain regions. Okay, I have to speed up a bit. So the same logic goes when we want to send currents to NEST. Only in this case, we have to pick up a different state variable that can be converted to a current and then use a different device of NEST that can generate DC currents. And similarly, with the connectivity weight and delay defined by TVB, send it to the spiking networks. The interface is very similar, only we need to change the device. So I won't go into details. And there is a last option, which is different than the previous ones. And it's a more special situation. Probably it can be used only with currents, in which case the coupling is for every target node that is modeled in NEST is computed already in TVB. So history, time delays are taken care by TVB. And then directly this current is setting a specific external current parameter that all neurons in NEST have at each time step. So here the logic is different because it's the coupling directly goes to NEST without any proxy node in between. Therefore, also the interface is similar. All we need to know is that we're going to transfer current, the target parameter in NEST, and the connections again, similarly as before. Finally, in case we have a bidirectional coupling and we want NEST to update TVB activity as well, then for every region that is modeled in NEST and we need to override the activity in TVB, We define spike detector devices that can detect all spikes that the populations of these regions emit. We can count them and generate an instantaneous rate, which then goes and informs, overrides practically, a state variable of TVB that has this meaning of instantaneous rate. Then we can do whatever we want with this. For instance, we can integrate it to act as a low-pass filter, etc. But this then has to be defined inside the TVB model for the moment. Right, and defining such an interface is again very similar. The important thing is to define the link. In other words, here we're saying, for instance, that the activity of the excitatory population should override the state variable of the instantaneous rate of that node. Everything else will work as for any other nodes in TVB. So this node will keep being integrated, will keep being generating any brain signals, etc. Very few words. In case the user uses the existing builders for the NEST network, then there are several steps. One is to define the populations one wants. Again, you can define as many as the user wants, and they will be generated sequentially. He needs to set a label, a default model, to decide on what nodes to place it, pass on any parameters, and define how many neurons should be there. And then one can define connections within a region among the different populations. For instance, here we define a connection from the excitatory population of a node to itself. And again, we pass on the parameters for NEST, the model of the connection, the connectivity pattern, possible weight and delays, receptor types for the synapses, and we define whether this kind of connection will be homogeneous in the whole brain or will be differentiated depending on where we are in the brain. Similarly, then we need to define connections among regions, and here is where we get informed from TVB. Again, from TVB connectivity for the weight and delay. Either we can set a number here as a weight or a function to take into consideration from which node to which node the connection is going to be. Everything else is pretty much similar. So always the interface looks like that. There is a builder and we give some properties in terms of dictionaries, and then it takes a few seconds to build the network. In a similar manner, we can define stimulus input devices like a Poisson generator here, and or devices to observe the activity of the NEST neuron, the NEST network to plot or whatever. And always we define a label that will help us get the results in the end, and give them a name and form time series out of it, labeled time series. And always we get a target population in S, so that we don't need to do any, we don't need to separate the data from what's neurons or what populations they're coming, because they're already labeled and we know exactly where we're measuring from. So I'm approaching the end. There had to be some modifications for the moment to the TVB simulator to work in such co-simulation. There are modifications for all models, like the simulator has to know about the interface. So there is a property there with a class of the interface. And also we had to introduce, the notion of non-state dynamical variables. In other words, variables that are recorded at every time step. It can be used as a target for NEST or to or as the source of the coupling to NEST, but that are not state variables, are intermediate variables that are computed at every time step. This was not there in TVB until now. And then obviously, and in the most, I would say, interesting applications, one could go also inside the TVB model and do additional modifications, like create specific variables that will, for instance, integrate the input from NEST or scale it or whatever else. As for the integration loop, for the moment, there is no parallelization. So at every loop, we have to do perform the TVB to spike network coupling, then integrate TVB for one TVB time step, integrate the NEST, usually with a smaller time step for more stability, and optionally update TVB with the spike network activity, and then do all the other steps that usually we do for TVB simulation, compute the coupling, and for the next time step, update this kind of variables, which are intermediate variables, and prepare for the next step anyway. So it goes serially for the moment, and this is also a kind of problem because we've done some benchmarking. And here you can see in the asterisk the time it takes to simulate whole brain with TVB only for 1 second. And then the time that it takes if we start substituting 2 regions with NEST and with increasing total number of neurons. In black, you see the total time. In NEST, you see the integration time of NEST as it increases. In green, you see the time for the communication from NEST to TVB. So the more neuron, the more spikes to count, etc. This can be sealed though, because the more neurons we have, we can just sample a fixed amount of neurons, and therefore it can stop increasing. And finally, there is the time for the communication from TVB to NEST, which for the moment depends mostly on how many different devices we create, and because they have to be updated at every time step, and this has some overhead. In general, there is a lot of space for improving this performance. For the moment, it was usability, the main target, and creating the concepts, but we are starting now to look into performance and how to parallelize and make things faster. In the last 30 seconds, I will show you a first result having during the validation process of the toolbox. So on the left, we have just 2 mean field nodes integrated in TVB, and on the right, the same 2 nodes in NEST. And there is a parameter sales exploration. On the horizontal axis, we have the global external excitatory coupling between the nodes scaled. And the different lines with different colors correspond to the recursive excitatory coupling. So the coupling between excitatory populations to themselves, actually. So the solid line, actually what you see here is a picture of bistability. Depending on the initial conditions, we get to a different attractor of a low activity or a high activity. And so in solid lines, you see the brands, the high brands, where we start from strong initial conditions. And in dotted lines, we see the brands of the bifurcation diagram, where we start from 0 initial conditions. And there is a big part always between the 2 lines where there is bistability, and the 2 are both stable. Now, what you observe here is that we get qualitatively, obviously, the same kind of dynamics, because the one model is a reduction of the other, and it's built to be like that. But on the other hand, we see that there are quantitative differences, like the actual values of these parameters are different, and also the scaling of the firing rates. So let's imagine now we wanted to really substitute some mean field nodes with spiking nodes. Obviously, it's not such a simple thing to do, right? Because in TVB in general, we care about the large-scale dynamics, and obviously here we just do the substitution, these dynamics will change. So last night I tried to hack it a little bit and just get the first result. I chose specific values for the W parameters such that the bifurcations are about at the same point. And I performed the simulation with 1 TVB mean field node and 1 NEST spiking node. And you can see that we recover pretty much the bifurcation diagram that is similar to the main field nodes. Yeah, this was more like a demonstration. Well, as I said, there is a lot of work to do. For the moment, we're focusing on validating this use case and the different interfaces I presented to you. in the way I showed you, we want to recover bifurcations of first and second order statistics. And at the same time, we're trying to optimize and increase the speed and the parallelization of the computations. And there are other things like improve the usability with the help of LIA in the cluster. And actually, for the moment, I'm the only user, but in the following days, I think we're going to have some new user and more feedback and space for improvement as well on real scientific problems this time. So these are the references. Thank you very much.